Welcome to part 7, radicals. I'm going to make some initial notes about this. And the first one is that reactions proceeding through a radical intermediate destroy chirality, and that means you get a racemic product. The second thing that I'm going to say about it is just list off the radical initiators, and those are HV, which stands for light in a certain wavelength. For most standardized tests, the exact wavelength is not important. Heat, and that's the symbol for heat, and peroxides, also written ROR. I'm going to go through a couple different parts here. Halogenation of an alkane, allylic bromination, the effect of radical resonance, the radical addition of HBr to a double bond, radical polymerization, and ozone depletion. I go a little bit more into mechanisms in this video than I do in my other videos, particularly because the ACS likes to ask you questions like, which of the following is a radical intermediate and a propagation step in, let's say, the addition of HBr to this compound right here? And they'll give you that would be the right answer. They'll give you a bunch of stuff that looks like that but isn't that. So I'm going to go through that sort of thing a little bit. They generally pop one question on there about polymerization and one about ozone, but those aren't too bad. So let's start from the beginning. When you halogenate an alkane, you're going to use Cl2 and a radical initiator to add chlorine, Br2 and a radical initiator to add bromine, and so on and so forth. You can use any of the radical initiators I mentioned at the beginning of the video. The initiation step is when you go from a non-radical to a radical, and in this it starts with chlorine. The chlorine breaks apart and each chlorine molecule keeps one of the electrons, and you get 2 of those. Then you start a series of propagation steps, which is when a radical reacts with a non-radical. In a propagation step will give you your major product, or another way of saying that is your major product will be the product of a propagation step. The reason for that is this reaction will spend most of its time propagating and terminate only a little bit of the time at the very end. Termination steps are where 2 radicals recombine, and you get a lot of different trace products in the termination step of a radical reaction, which is why they're commonly called unpredictable, because you get things like CH3CH3, which you didn't exactly want. You just wanted to halogenate your CH4. That's all you wanted. But you don't get that, so now you have to separate it, which is an extra step. Chemists don't like extra steps. Alright, the first propagation step I've labeled A. The chlorine abstracts a hydrogen, and you get hydrochloric acid and that CH3 dot. Then the CH3 dot reacts with another Cl2 to give you CH3Cl and Cl dot. You also get the major product in a termination step, but that'll normally happen, but most of it is made during this propagation step right here. That's why I have a little star by it. Other termination products are Cl2, CH3, CH3, and anything else you can think of that's a permutation of the different radicals you have here. They can recombine in any way they want to. So if you are trying to pop a halogen on something that's not as simple as CH4, where you might have primary, secondary, and tertiary carbons, you have to do a little math. I know we all love math. These are the speeds at which, for bromination and chlorination, the Cl dot or the Br dot will selectively go toward these 3 different types of carbons. Starts with 1. Bromination is pretty exclusive in the sense that the tertiary product will form 1,600 times faster than the primary product. So you're going to get essentially no primary product ever, even if there's a secondary carbon in there, because that forms 82 times faster. I mean, like, that's like me crawling and trying to race, I don't know, a fighter jet. It's just not going to work. Chlorination is a little closer, 1, 3.8, and 5. And by closer, I mean you have to start looking at the number of hydrogens that are primary, secondary, and tertiary, and multiply the rate by the possible number of chances that you have to abstract that hydrogen. So in this problem, for example, you have 1 primary hydrogen and 9 tertiary hydrogens. Or I said that completely backwards. 1 tertiary hydrogen and 9 primary hydrogens. So 9 is the number of chances you have to abstract the hydrogen. Multiply that by the rate at which it tries to abstract and you get 9. You have 1 tertiary hydrogen. Multiply that by the rate it wants to abstract the tertiary hydrogen and you get 5. If you had 14 of these molecules reacting, you'd get 9 of them that abstracted a primary hydrogen and 5 that abstracted that one. So your primary product would actually be, your major product would actually be a primary alkyl halide. So you got to think about that when predicting the major product. Now we're looking at allylic bromination, and this is benzylic as well, just 1 carbon adjacent from a double bond. The initial way to think about this is something you've seen before. Say, what if you just use Br2 in light and thought to yourself, well, Br is pretty exclusive. It wants, just like a carbocation, it wants to form, to go to the most stable thing, and allylic is pretty stable. Wouldn't it go there? Yeah, it would. You'd get some of that product. But the problem with that is that reaction would be in competition with the reaction you learned in Orgo 1, which is when you have Br2 in just a solvent of some sort and add it twice to a double bond. So you'd get a little of that too. It'd be pretty contaminated. So what you do instead is they came up with this nifty thing, NBS ROR, or you can use light instead of ROR, or I don't know, heat. But you see NBS ROR a lot. And that is a specific reagent that only does this. It's pretty sweet. It's N-bromosuccinimide, but you just see it written NBS. So use that. I'm sorry, but you're going to have to worry about resonance. And it's a little different because individual electrons are moving, not pairs of electrons. So what you have happening here is the first step is hydrogen abstraction in any of these. So the NBS pulls off that hydrogen that is allylic. And then that hydrogen can combine with one of the hydrogens from this double bond, and the other hydrogen kicks off onto that carbon, making this guy. And they resonate back and forth until the bromine attacks. And depending on which structure it's in or closest to being in, when the bromine attacks, you're going to get one of 2 products. And I've shown those 2 different pathways in different colors for you. They're different in this case because you've got this thing over here that makes the molecule not symmetrical. So, yep, different. Got to worry about that. Radical addition of HBr to a double bond. We've already added HBr to a double bond. When you add a radical initiator, it just makes it anti-Markovnikov. And this is a reaction you should already be familiar with, adding right there. In this case, it adds anti-Mark. Now, I've included the mechanism for the same reason, because they might ask you about the what's a propagation step? So the initiation step is the ROR breaks up into 2 RO dot. The RO dot abstracts a hydrogen from the bromine to make ROH, an alcohol, and Br dot. The Br dot adds in such a way to leave the resulting dot for the radical on the most stable place. That abstracts the hydrogen back from the ROH, because RO The ROR is a catalyst, so it's going to be regenerated. You get your major product and a propagation step, plus RO dots. The RO dots recombine somewhere in the termination step. And again, just think of all the possible radicals you can make during propagation and combine them in all the possible ways and permutations, and you'll get all the possible termination trace products. Radical polymerization, not a huge part of any standardized exam, but still a part nonetheless. I is a general symbol for a radical initiator. I dot, that's one of these guys, or just a radical that initiates stuff. If you put that in with an alkane that has non-aromatized pi electrons, or an alkene that has non-aromatized pi electrons, chaos will ensue. You're going to have a confusing day. First, it breaks this up, puts tacks an initiator onto one end of it. Imagine RO or maybe BR dot or something that's initiating this. And it puts that guy there, which will attack another. Do the same thing. And you just keep tacking them on and on and on until you build a big old chain. And that is written, after that combined, you would have a repeating unit right here. Ignore that I, but in the middle it would be mostly hydrogens, but terminal ends would be a little different. And it would just keep going. So you put brackets around it and put N, because there's a lot of them. N is just any number of them. Just a ton of those. And that's a polymer. You make PVC that way. Well, I mean, this isn't PVC. PVC is something else. This is styrene polymerizing into some weird chain. Ozone depletion. Ozone is O3. It protects you from the sun's radiation so you don't get sunburned. This is a chlorofluorocarbon. Yeah, they're pretty bad for ozone, and ozone depletion is just why they're pretty bad. So that puppy is lighter than air, floats up into the upper atmosphere, gets hit with the UV radiation, gives you a chlorine radical. Chlorine radical reacts with the ozone to give you ClO dot and O2, thus destroying your first ozone. The ClO dot destroys another ozone to give you ClO2 dot and O2. That ClO2 dot just degrades back into Cl dot and O2, and that Cl goes right back into the cycle. So it's pretty bad for your ozone. Well, that's it for number 7, radicals. I will see y'all next time for number 8, the reaction of benzene.